reading. Oh, I've mentioned this before to you guys in the last, before we left. I'm going to want you guys to read your textbook. Okay. Because a lot of this is more theory stuff than actual math. I think you guys are going to discover the calculations for some of this stuff are really easy. Well, that's not the point, though. It's being able to interpret the theory behind it. So, okay, let's get started. Have I talked with you guys before about the 4 main types of forces that physicists have discovered? You don't need to know this unless you go like way on in physics, but there are 4 fundamental forces. One is gravity, which I think you guys are all familiar with. Another one is the electromagnetism force, which is kind of what we're exploring in this unit. And the other 2 main types of forces are what are called the weak and strong nuclear forces. Weak nuclear forces basically involves like gamma and alpha and beta decay, where particles will actually break down and emit off like electromagnetic particles. Does that make sense? We actually talk about this in our 3rd unit. The last one is called a strong nuclear force. This is the strongest force, I believe, that there is. Think of the nucleus of any sort of atom. In the nucleus, you've got neutrons and you've got protons, right? Protons are all positively charged particles. Do positives want to stand next to other positives? So ideally, what should happen is a nucleus should want to just blow itself up, right? Because all these positives, all peppered inside there, would not want to be next to each other. And that's where this strong nuclear force comes in, is it somehow keeps all of those positive protons together. Does that make sense? Because otherwise, you'd have nucleuses wanting to break apart. So, anyways, I just wanted to bring this up because electric charges and gravity charges are 2 of like the main fundamental forces that we have. Okay. I have some other bolded words here I'd like you guys to know. One of them is called a contact force. Okay. When I'm sitting on the table, there are forces between me pushing downwards on the table and the table pushing upwards on me. Does that make sense? If I throw a ball, that's me being in contact with things. Physicists have known about contact forces for a long time, but sometimes there are forces that occur and we call them actions at a distance. Well, like gravity right here, if I let go of my pen, is going to cause the pen to fall down to the ground. But is anything actually touching this pen once I let it go? And you say, well, no. And it's kind of the same thing when we get to magnets and get to electric charges, is they don't actually have to touch each other for there to be either attraction or repulsion. So there's just some words I'm hoping you guys will recognize. Action at a distance and contact forces. To try to explain the concept then of why forces exist when things don't actually touch each other, a guy named Michael Faraday came up with the idea of a field. And we talked about fields in Physics 20, but like briefly. Like I mentioned the word once or twice and we moved on. So I want to talk more about them today. A field, like if you look up a definition in a textbook, it's described as like a region of influence. Okay. It kind of sounds like a social studies kind of term. Because you guys talk about stuff like that in social studies, right? Not you don't call it a field though, but you talk about like spheres of influence maybe, or buffer states or something. I don't know enough about social studies. But concept here being that any object within the field is going to be affected by the field. So, are you affected by the gravitational field of Earth? Absolutely. You're really close to Earth. Is Mars affected by the gravitational field of Earth? Slightly. You're really far away. Mars is really far away from us, right? But I mean, there still is a little bit of field strength way out there at Mars. This pen and I am in the gravitational field of this pen. But is it a particularly strong field? I'm really close to the pen. Why is the field of the pen not that strong? Yeah, because the pen is really small. Okay, so some fields, I guess you could argue, they extend indefinitely. But as you get further and further away from the object that's making the field field gets smaller. Does that make sense? I've got some more definitions for you then. One is called a scalar field, and one's called a vector field, which you guys know those words, right? Direction matters or it doesn't. So, let me give you another example of a field then. A fire. It's kind of a field. As you're really close to the fire, it's really warm. There's a lot of heat there, right? And so it's emitting a lot of energy. Energy is measured in joules. But does energy have a direction? No. So energy or heat would be considered a scalar field because, sure, I can measure how much degree temperature there is. I could measure how much joules of energy there is, but we don't normally attach a direction to those sorts of things. Another example of a scalar field would be a sound. Another good example. A source that's emitting sound. If you're really close to that source, you hear the sound very loudly. What do we measure sound in? What units? Yeah, decibels. Yeah, is a good unit for measuring sound. As you get further and further away from the source of that sound, the field strength of those waves gets smaller and smaller. But do we normally attach like a direction to sound? So those are scalar fields. Gravity, though, is an example of a vector field where we actually have to give a direction. Sometimes the direction is like up or down or east or west. Sometimes, though, we might just say in or out. That'll work. So, one really important note I want to put down here. Field strength and force amount are not the same thing as each other. And that's one thing that I realized after marking some of your guys' tests in Physics 20. I don't think I hit on that enough. Field strength, like for gravity, was G, little g. Okay, what's the field strength on Earth for gravity? Yeah, 9.81 meters per second squared. That's the field strength on the surface of the Earth. That being said, what's gravity's field strength further up or somewhere else? It might be different, right? Okay. But that is not the same thing as a force amount, which is like Fg, which we calculated by doing mass times the field strength. Does that make sense? So those two things are very different. So you have to make sure that if I ask you for the force involved, that's the capital F type formula. And if I ask you for a field strength, that's something different. How do I want to describe this? You guys ever seen diagrams like this where they have like lines and arrows pointed everywhere? Ever shown you one of these? These are called vector field line diagrams. And basically the short answer for how these things work is that it's based on a positive test charge. Okay? You'll notice that all of these arrows are pointing a certain direction, and they're always pointing towards the negative. Does that make sense? So like this is pointing in towards the negative, in towards the negative, in towards the negative. Even as it's going out this way here, ideally it'll eventually loop back around and then come in towards the negative. So field lines are always drawn. Oh, I lost these guys. Lines are drawn from positive to negative. Sorry, you guys might have to bear with me for a second. Oh, there we go. You guys able to hear me again? Perfect. Okay, I don't think you missed a whole bunch there. I wrote it on the top of the screen, so picking this back up again. If you ever see these diagrams here, I want to explain those over the next few slides. Basically, the idea is we by default draw field lines from positive to negative, so the arrow always points towards a negative charge. That's just like our default setting. They chose a proton to be like what they call a test charge. I think they could have picked an electron. Like sometimes you just have to pick one and you're going with that from now on. So I don't think there was any reason to it. So I have a whole bunch of notes based on this that I guess maybe I'll just read them out here. In order to detect an electric field, the easiest method was to place a known charge nearby and figure out how it reacts. So you'd use what's called a test charge. Holy smokes. Thanks. Yeah. You did. Okay. They were wondering whether you were here. Yeah. I know. Alright. Okay, the idea behind this test charge would be to have an infinitely small, impossibly positive charge. So, I mean, we're talking a hypothetical situation here, because you can't make like something infinitely small. But the idea would be then to make something that has no electric field of its own. And so here's the basic idea. If you have a positive test charge and it moves towards the unknown source charge, the unknown source charge needs to be negative. Why negative? Perfect, the opposites attract, right? So if you have a positive test charge moving towards an unknown object, the unknown object needs to be negative so that they actually attract each other. Whereas if a positive test charge moves away from another one, it must also be positive so that it is repelling each other. Does that make sense? So, long story short, by definition, we're going to pretend that when we're drawing these field lines, we're going to pretend we're a proton. So as a positive charge right here then, you're going to want to draw everything away from a positive charge and everything towards a negative charge. You guys got that? Move on. So, you can have more than one charge in a diagram. It just means that often you have like positive going towards negative. You know, so everybody sucks in towards the negative object. Everybody pushes away from the positive object. You could even have two positive charges. So what's happening here is everyone is trying to push away as far as possible from the positive charges based on field lines here. And you've almost got like a big chasm in the middle here where really positives don't even want to be there at all because they're trying to get pushed away. Yeah.
What's the point of these diagrams?
Basically just to describe what a field looks like. Like, so imagine that you were to drop a proton right here all of a sudden. What would happen to it? It would go that way. That makes sense. We've done this before with like gravity. If this is an object here, like this is Earth, you know, everything gets sucked into the middle of Earth. Doesn't really matter where you are in space. So it's kind of trying to describe basically what would happen. Does that make sense? Okay, I got more diagrams, but hopefully you guys have the concept here. So let's get on to the math. If you want to figure out electric field strength, so we're not talking a force now, we're talking a field strength. So kind of like with gravity, the field strength of gravity on Earth is 9.81 meters per second. If you want to figure out the equivalent of that for electric charges, here's the formula. It's capital E, this is going to be confusing, is equal to the force you have divided by Q. Okay. You're going to hate this. This E right here, since it has the little like vector symbol on top, it means that this is electric field strength, not energy. So confusing. You put the little line over top, it's field strength. You take the line off, it's now energy. So stupid, hey? Why does energy not have a little line over top of it? It's not a vector. Yeah, it doesn't have a direction. Energy is vectorless. So E with the little hat means field strength. Oh my goodness. Field strength. E without a line, energy. So you're going to have to be really careful with some of these formulas here because there is actually a formula we're going to learn tomorrow which has energy involved. So sometimes you got to be just, anyways. One more thought here. You also need to make sure that you use the right Q value. This Q is the charge on what we consider to be the test charge. Okay. The test charge itself is not the one emitting the field. So we have to divide by the test charge because we don't actually want to account for the one that we're testing it with. We want to calculate the field based on the other object. So let's do some questions. You have a 3.7 Coulomb test charge placed 2.7 meters to the right of another charge. I'm going to give you a force. Let's figure out a field strength. So, how do you calculate field strength? Well, field strength is E, and I'm going to make sure I put that vector hat on top because that makes a big difference. That is equal to your electric force divided by Q. Do I have that electric force? How do I know? And one more thing, I guess. Forces are measured in newtons. So this is 3.62 times 10 to the 10 newtons. Then we have to divide by a charge. We have to make sure we divide by the correct charge. So we're dividing out the object that we're testing. That makes sense? So we actually are looking for the field strength based on this guy. So this guy is the test charge, so this is the one that we're going to divide by. Does that make sense? So 3.62 times 10 to the 10 divided by 3.7. So I got 9.8 times 10 to the something. 3, 6, 9. Okay, so the units for a field strength is a Newton per Coulomb. I think I had that written on the last slide. Yeah, electric field strength units are newtons per Coulomb. Okay. One more thing, this was a vector. And so as a vector, we need a direction. So if we have a positive test charge and the source of the field is negative, which way is the field going to make us go? Is it pulling us in or pushing us out? Okay, so some sort of direction being like pulled inwards. Does that make sense? Because it's an attraction as opposed to a repulsion. Hello. If you were to have like a diagram, you'd have like your negative charge right here, and then your positive right here is being pulled inward. Anybody want breakfast? Mystery box. It looks like we're good. Thanks, guys. That makes sense? So I just drew a quick diagram here. So what you have is this negative charge right here, and the negative is a negative 7.94 coulombs. That number was irrelevant. But the reason I'm drawing this diagram is just to point out that your positive test charge would be pulled inwards towards this guy. And this is the strength at that particular point. I found this slide somewhere. It kind of shows the similarities between gravitational field strength and electric field strength. So gravitational field strength is little g. And if you wanted to find that, you could take Fg and divide by mass. Because really like Fg is like mg. You divide, you cancel them out. So this is kind of the same concept here. Here you divide by mass. Well, here you divide by charge. So this is electric field strength. Let's do some more examples. You have a positive test charge of this. Let's put in an electric field. Let's figure out the force exerted. So electric field strength is equal to your electric force over the amount of your test charge. We're looking for force, so we need to multiply up the Q. So this is 2.3 times 10 to the 3 newtons per coulomb. the charge of the actual test charge is 3.7 times 10 to the minus 6 coulombs, what's going to happen with your units? Yeah, hopefully you can see they're going to cancel, right? I got 0.00851. So that's going to be 8.5 times 10 to the minus 3 newtons. One more thing though. Force is a vector. So I'm going to need a direction. So if the electric field pushed us outward, it would be fair to say that this is still getting pushed out. I don't care what word you use, out, in, towards, away, but just make sure you include some sort of word to indicate whether or not you're getting pushed towards the field or away from the field. Straightforward still? Would you agree with me when I tell you that the math is actually going to be about as simple as you can imagine? Like, it's very straightforward, plug it into formulas, but you just have to know which formulas to use. If you have your data sheet nearby, there's a few other formulas you may see on there. Here's the one that I just started working with. This one right here is Coulomb's law. If you kind of were to combine them together and take this and plug it into the one we just worked with, you see how you'd get E would equal K Q1 Q2 over R squared over an extra Q if you took this and like substituted that up top here. Does that make sense? We've kind of done this before with our gravity unit, same concept, because what would happen is one of your charges would cancel now. And what you'd be left with is this formula here. Only one difference. In this formula here, the Q is now the source charge because you've canceled away the test charge. You got to keep those straight, eh? Does that make sense?
Well, what's the difference between the test charge and the source charge?
Okay, so imagine that this is gravity rather than electric field strength. Here is a water bottle and here is me. Okay, I am emitting off a gravitational field. So I am the source and the water bottle is the test. Does that make sense? So like in terms of gravity, really the Earth is the source of gravity and you are the test object for it. Make sense? So this formula, I prefer this one myself because rather than working with an arbitrary test charge, what you actually need to know is the actual charge that is emitting a field. So you just have to use a different Q. Again, you just have to know how the formula works and keep everything straight. So let's try another example. You have a tiny metal ball with a charge on it. We want to figure out the magnitude and direction of the electric field it produces a random distance away. So if I were to draw a diagram here, here is a ball, and it has a charge of -3 times 10 to the minus 6 coulombs. Right off the bat, if this thing is a negatively charged object, which way is the field going to be pulling or pushing? In or out? In. Because we've defined a field as whatever direction something positive would go. So if this guy is a negative, positives would get sucked in. Does that make sense? So right off the bat, I know that my answer is going to be in something. We're going to be 30 centimeters away. Does it actually matter whether we're 30 centimeters away above or below, or doesn't make a difference, does it? So using the formula we just derived then, to find an electric field strength, you need to know K. You need to know the charge of the actual object producing the field, and you need to divide by the distance squared. So, what's K? Good. Yeah, it's that 8.99. It's Coulomb's constant. Times 10 to the 9. Oh, what are the units now? Coulomb? Nope. Coulomb's goes on the bottom. Newtons meters squared over Coulomb squared. The Q is now the actual charge of the object producing the field. So this ball right here is causing objects to get sucked towards them, I guess. So that is... Do I need the negative? the negative just tells us which direction it goes. So 3 times 10 to the minus 6 coulombs. And then on the bottom we need to have our distance, but it has to be in meters. 0.30 squared meters. So I guess I could write it like this. That way the meters will cancel. One of the coulombs will cancel, and we'll get a unit in newtons per coulomb. So. I got this 299666 repeating. Anybody else? Okay. 299 and then 6 is going on for forever. So I guess if I round this, it's going to be 3.0 times 10 to the 5 newtons per coulomb, and the field is defined as what a positive object would do. So really, we just have a random negative object sitting out there. Anything positive would get attracted to it.
You're living your flex box.
Excellent.
There's timetables for everybody. You get those out.
Okay.
10-inch sheet, just give that back to Charlene.
Okay.
And the sheets if you're sending them.
Good. Thanks. That makes sense. I hope you'd agree. The math is really straightforward. Like they're not hard formulas. You just have to understand when to use what formula. Let's try another one. Find the electric field strength exactly in the middle of these two charges.
So would you split the distance in half?
We're gonna have to split the distance in half. So how far away is it from the one object?
0.29.
And then 0.29 meters away here. Now both of these are negative charges. So imagine that we had a proton, just a positive charge. What would happen to this proton? Well, according to this guy right here, he'd get pulled that way. But this guy over here is also negative. So he'd get pulled this way. Who's gonna win? Yeah, the bigger charge will probably win, right? But we're gonna have to actually calculate that. So what we're gonna do is we're gonna find the electric field strength based on this guy. We're gonna find the electric field strength based on this guy, and we're gonna subtract the two field strengths. So it's not actually that hard, it's just double the work. So electric field strength is equal to, what is it, 899 times 10 to the 9 Newton meters squared over Coulomb squared. This guy's charge is negative 1.2, although, do we need the negative? We don't need the negative. And then the distance is 0.29 squared. I got 1.2827 times 10 to the 11. So, what I got then or no?
Yeah.
Oh, okay. Okay. So in terms of direction though, this would have been pulling it that way, whatever way that way is. So I guess left. Does that make sense? However, there is another electron which would pull something to the right. So I got to do the exact same work. I'll just pull this down here. This electric field strength is equal to 899 times 10 to the 9 newtons meters squared over coulombs squared. This guy's charge was 3.9 coulombs. Same distance. On this one, I got 4.16896 times 10 to the 11 newtons per coulomb. Okay, but this one would be pulling you to the right. It would be pulling you this way. So last step, take your two field strengths. Field strengths are vectors. So if one is pulling you left and one is pulling you right, subtract the two. So 4.16896 times 10 to the negative 11 minus 1.2827 times 10 to the 11. I got a final answer of how many sig digs do we get? 2? 2. I got 2.9 times 10 to the 11. Who wins the fight? Which way is it going, left or right?
Right.
Okay, good. Does that make sense to everybody? Awesome. I think I have one last example. Is that the last one on there?
Or are you doing this?
Yeah, the last one there. So I have one last example. Yeah, we'll do this one together as a group, I guess. What's the change now? Now it's not in one dimension. Now it's like in 2 dimensions. So it's really not that different than any momentum question we did, than some of the forces question we did. When we're done finding our electric field strength, we're going to have to break it up into x and y, figure out how the x's and y's work with each other, and then when we're done, we're going to have to remake a resultant triangle. That make sense? So it's a lot more work. So, here's a test point. This guy is negative, and this guy is positive. I just want to draw some field lines to begin with. If this test point is always defined as what a positive charge would do, it would get pulled towards this guy right here. That makes sense? But if this guy has a positive charge, at this particular point, he's going to get pushed away as well. So what's going to happen? He's getting kind of pushed up, but he's also getting pulled down. So we got to figure out which way he's actually going to go. So I don't actually think I know exactly where it's going to, like which way it's going to go. I think it's probably going to go this way-ish. I don't know exactly whether it's going to be, directly to the left or not. So first, let's just find how much field strength each of these things has, though. So I'll do it for this guy. Let's find the electric field strength based on A. Okay, so 899 times 10 to the 9 times by, is that 210? 210, 10 to the negative 6, all over 4, 10 to the negative 2 squared. Okay, I got 117,99375. Yep. Okay. In terms of a direction, though, maybe it's best if I just say that this is getting pulled that way. I'll worry about the actual specifications of that later, but this field strength is pulling it in towards the blue ball. So, then I also want to do the field strength for the red ball, so it's like the exact same stuff. Only this was 1.5 times 10 to the minus 6. And is that 3 times 10 to the minus 2? 3 times 10 to the minus 2 squared. What is that, 1.50 times 10 to the minus 6? Okay, this one I got 1, 4, 9, 8, 3, 3, 3.
You got what?
1, 4, 9, 8. Oh, hang on. 4 threes. You guys get the same number as me?
Yep.
Okay. Now, based on the positive negativeness here, this guy, his field would make a randomly chosen proton go up and to the left. So I'm just going to draw an arrow that way just to indicate that's what's happening. Because now I need to break this up into like triangles. So do this one at a time. This guy right here has an angle of 36.9 degrees. And if this guy is going like that direction there, there is some in the y direction that is pulling down, and there is some in the x direction that's pushing that way. And I've got to figure out the x and y components. And this number is the hypotenuse. That make sense? So I now need to figure out the electric field strength for A in the y direction, and I need to find the electric field strength for A in the x direction. So this one is going to be, this will be sine, and this one will be cosine. 117,99375 times the sine of 36.9. Alright, so here I got 7, 0, 8, 4, 5, 8, 3. Should be enough digits. This will be cosine. Here I got 9, 4, 3, 5, 7, 7, 9 newtons. Anybody else get the same values as I did? Does that make sense what I'm doing? So I've been given now a hypotenuse. With the hypotenuse and the angle, I'm going to break it up into x and y directions. And so part of this thing is getting pulled down, and part of it is getting pulled left. Now I've got to do the exact same thing for the other triangle, which is actually getting pulled left but also up. So this guy is going that way, which means part of it's going there, part of it's going there. And the angle, was that 53.1? That guy's the hypotenuse. So same thing, I now need to find the, I should put vectors on top of these. The field strength for B in the y direction, and the field strength for B in the x direction. So again, this guy will be sine and this guy will be cosine. Alright. 1498333 times the sine of 53.1. So here I got 11981 and this guy would be going up. And this one is 8996296 newtons left. You guys still with me? Alright. Okay, so I've broken everything up into X and Y direction. I mean, I'm calling them left and right. I don't care what you call them. Just make sure that it's clear, like so that someone can follow your work. Mainly you. Once in a while, me when I have to mark it. Helps when I can see what you're doing. Okay, last step. We got to figure out how the X and Y directions are going to work now. So in the X direction, one of them was going this way, and then the other one was going this way. So we're going to want to add them together. So that's going to be 9, 4, 3, 5, 7, 7, 9 plus 8, 9, 9, 6, 2, 9, 6. Boy, these numbers are stupid. So I've got a grand total of 1843, 2075 newtons going that way. That's your X direction. So a lot of, hang on, this isn't actually newtons, is it? It's newtons per coulomb. Sorry, change all of those to N over C. This isn't a force, this is a field strength. So there's a lot of field strength wanting to push things to the left. In the Y direction, one was going up and one was going down. So the up one was going 1198191. And the one that was going down was going 7084583. So I got an answer of 4897358. And it looks like up is stronger than down.
So we do it, there's also kind
And that's our lesson. Like I said, this might feel familiar because really we did the same thing in momentum, we did the same thing in forces unit back in physics 20. Heck, we did the same thing with that Coulomb's law formula a while back too. I would expect, and I don't know for sure, but I would expect on the diploma exam that they probably might ask you one question to solve in the X and Y directions. I wouldn't expect that every single topic is going to involve X and Y because it's a lot of work, right? Chances are they're just going to ask you linear questions because like the one we did above this is a lot easier to do, right? When you've got to do this in X and Y, it's crazy. Okay, so the field goes down, the field also goes up. So if this is our test point, it goes, let's see, 18432.075 that way. Goes 4897358 that way. By the way, is anyone double checking my numbers to make sure I didn't screw up?
of. Yes,
Okay, good. Oh yeah. Alright, square that, add 184.
Please excuse the interruption. High school teachers, the flex block, priority 1 flex block is now beginning. So students, you should be in your priority 1 flex block or have a slip from your teacher telling them where you're going. Also, just a reminder that the ski trip, due to the fact that Castle Mountain is closed, has been canceled for the year. So the ski trips for the year have been canceled. High school priority 1 flex block is beginning now.
Wait, so flex block is an hour then?
Yeah.
I was like, if it's just half an hour, once you're out of track, it's the same for like.
I got 69 degrees in the corner there. You guys get the same thing? So, final answer then, after all of this work, how many sig digs do I get? Looks like 3. Oh, I need to keep another sig dig here then. I got 69.4 degrees. So the field strength is 1.91 times 10 to the 367 newtons per coulomb, and it's going 69.4 degrees, I don't know, north of west. So, if I were to redraw my object right here, this test point right here, the field line would be going that way. So, a proton would want to get pulled that way. It would want to get pushed this way, but at the end of the day, it's actually, it looks like this one here wins out considerably. So it would actually end up going kind of that way when you're done. That makes sense? All right, go take a 5-minute break. Come back in 5.
Is that